Hi everyone, today we are going to talk about the last part of Unit 9, which is about regression equations. In this video, you're going to learn how to determine the type of function that best represents a set of data. We're going to use a calculator to determine the curve of best fit, and then we're also going to make predictions about future data using that curve of best fit. So let's get started. First, we need to talk about a scatter plot. Whenever you have a graph that has two variables plotted along two axes, and you plot a bunch of data as ordered pairs, that's a scatter plot. And what we're looking at when we look at scatter plots are patterns with the points, or like a shape that the points are making. Because if we can look at generally a shape, that's going to describe a correlation or a relationship between the two variables that you're working with. So let's talk about a scatter plot. So if we have a fan throwing a souvenir football into the air from the top of the bleachers, the table shows the height of the football in feet above the ground at various times in seconds. So we have the x variable is the time, and then the dependent variable, depending on what time it is, that tells us the y variable, which is how high the souvenir football is or isn't to the ground. Now, I just want to take a step back here before we plot these points and just think logically about this situation for a second, not within the context of a math class. So if I have a little person down here and I have a bunch of bleachers, oops, I'm having trouble this morning. All right, a bunch of bleachers, and I'm throwing a souvenir football. I'm going to release it from my hand, it's going to go up, and then it's going to come down, right? That's the football's path. That shape is what we're looking for. We're looking to see, and hopefully this data will follow. Do you notice it's kind of a U shape, a parabola? That's what we're expecting to see based on the context of the problem. So let's see if the data works out that way. At 0, the y value is 10. At point 2, it's 11.76. At point 4, it's going to be 12.24. At point 6, it'll be 11. Goodness, my computer's not happy with me today, guys. Let's see, so I've got to do point 4 again. That puts us there. And then point 6 puts us down at 11.4. And then point 8 is at 9.36. And 1 second in, we're all the way down at 6. Okay, so we have our ordered pairs plotted there. And do you notice that the shape of that does look like what we were talking about when we were just imagining throwing a souvenir football. So when we want to find the curve of best fit, that just means draw the best line possible or the best curve possible for this data set. So we need to consider our interior behavior. And what I mean by interior behavior is where is it increasing or decreasing, and the shape that it's making. So in this picture, we have a U-shaped looking curve, and if I was going to draw a line that kind of best fits these, I'm going to try to draw a smooth U shape, but I'm going to try to hit a bunch of the points. And if I did that, roughly, approximately, that would be my guess at the curve of best fit, or the parabola that fits the data. So you'll notice here that at first the scatter plot was increasing. It was going up, then it hit this vertex point, and then it started decreasing. So because it was increasing then decreasing, we are looking at a parabola. The scatter plot increases, and then that changes to decreasing, and it makes a U shape. So this says to me quadratic. So then if I want to approximate the height when of the football when x is equal to 1.1. All right, so I'm going to look at my x-axis, and I'm going to go to 1.1, which is here, and I'm going to go up and see right there looks approximately where it would be on my line of best fit, and that y value looks like it's 5. So I'm going to say that the height is going to be approximately 5 feet based off of this really rough sketch that I did. So these really rough sketches are nice, but it's kind of a lot of work to plot a lot of data, and then you're not super accurate because this is just kind of a guess based on the steadiness of your hand, your ability to draw the shape, and all that kind of stuff. So we're going to look at how the calculator can help us do that today. Now, the first thing we want to be able to do is we're going to plot the data in our calculator using a table or in Desmos, and then we need to be able to identify which function to use. So let's look at these three before we plot the data in Desmos and just worry about shape and function. So when I look at this first one on the left, I see a bunch of dots that are generally an increasing line. Roughly speaking, the data is going up like that. It's a straight line. It's not like a crazy squiggly anything. It's linear. Because it is linear or a straight line, we're going to say that the parent function is linear. This is algebra 1. Remember you had mx plus b, right? So it's going to be a graph using a linear function. Now the second one, it looks kind of wonky, but we're roughly looking at some kind of U shape there. Because it's a U shape, or because it goes up and then down, increasing and then decreasing, that's going to be a quadratic function. And this last one, I can't just draw a straight line to hit these points. It's got to be kind of this curve that looks almost like a hockey stick. And that kind of hockey stick shape, that's an exponential function. These three types of functions are the ones that we're going to be focusing on in Algebra 2 this year. So we need to be able to identify shapes that are linear, quadratic, or exponential. Looking at the interior behavior, increasing and decreasing, and also the shape that it's making is going to help us make those decisions in addition to the context of the problem, like we talked about when we were doing that rough sketch. Okay, so let's get into getting the calculator to create these better curves of fit for us. So when we're doing this in the calculator, it's called a regression calculator, or a regression equation. Basically, we're going to have our data input into the calculator to make a scatter plot, and then we're going to tell the calculator what type of function we're expecting to see. Is it exponential? Is it quadratic? Is it linear? And it's going to give us the equation for that data that we've given it. So we do need to know the formulas in standard form for linear, quadratic, and exponential equations. I've given you in this first row here the equations that you should have memorized from the units where we've worked on these. You'll notice in the second row, or the last row here, that a couple of things have changed, but this is what we're going to be putting into Desmos. Notice that the x and y variables all have a subscript of a 1. That's going to be very important. That subscript happens in all places where you put an x or a y. You have to say use the first x, use the first y. The other thing that I want you to notice is that instead of an equal sign, there is this symbol. It's called a tilde. It's kind of that squiggly sign. It means approximately here. So because we're approximating or guessing the curve of best fit as accurately as possible, y isn't equal to this line, it's approximating it. The rest of each of the formulas is the same as the equations that we've looked at in standard form when we did these units over the course of the year. So let's get into Desmos. In this first example, or example 4, a pumpkin tossing contest is held each year in Morton, Illinois, where people compete to see whose catapult will send pumpkins the farthest. One catapult launches pumpkins from 25 feet above the ground at a speed of 125 feet per second. The table shows the horizontal distances in feet the pumpkins travel when launched at different angles. So depending on what the angle is, it will travel a different distance. So we have our x and our y. We are going to first add a table and enter it into Desmos. So I'm going to pull up Desmos here. To get a table, you're going to click this plus sign that says Add Item, and then you're going to go down to Choose Table. Now from here, remember how I said there were those subscripts of 1? Notice that this table has x of 1 and y of 1. That's because if I add another table, so that Desmos doesn't get confused, it's going to call this my second table and have x of 2 and y of 2. So we only need the 1, but whenever we use x and y as variables in our equation or in our formulas, we're going to need that 1 so it pulls from this table. It doesn't get confused. Okay, so I'm going to do my x's first. I'm going to put in 20 just by typing and then hit enter. Then I'm going to type 30. Now look at what Desmos is doing. It followed my pattern and is now going to let me, if I hit enter, continue to just cycle through until I get to 70, which is where my data stops. If you use the arrow to go down, it will not continue. So I'm hitting enter for it to automatically populate. Okay, so I have my x's. Now I need to put in my y's. So I've got 372, enter, 462, enter, 509, enter. Notice here that as I'm doing this, it's not auto-populating because this time the y values aren't following a particular pattern. There's not a arithmetic or geometric sequence or anything like that. So it's not able to predict for me what the numbers are to come. Now, I would absolutely always check your work. Make sure you don't have any typos, because any typos you have here is going to doom the rest of your work. You need to have your data entered correctly. So looking back, it looks like everything is okay there based on my table. So now I'm going to click this zoom fit button. It's a magnifying glass with a plus sign, because you'll notice this when I put in this table, I didn't get any points on my graph over here, and I really want to see a picture. This is going to zoom and fit to my picture. I'm actually going to change my settings here a little bit so that it's easier for you to see what's going on. Okay, so I have my data set, and now I want to look at figuring out what the parent function is. So I need to look at my shape, I need to look at my context in my problem, and I need to look at my interior behavior. So this one is increasing and then decreasing. The shape looks like a U, and remember our problem was we're basically throwing pumpkins from a catapult, or catapulting them across a field. So the pumpkin's going up and then it's coming down. So again, all three of those pieces of information show us that we are looking at a quadratic equation. So we are going to identify the parent function as quadratic. That means then that we're going to be using that standard formula for quadratics. Okay, so we are on step 3 now. We are going to go back into Desmos, and now we are going to, on a new line, put in the Desmos version of the formula for quadratics. So I'm going to say y, and then I need to get that subscript of a 1 like my table has. So I'm going to hold down the shift button and push the hyphen key, which is right beside the 0 key at the top of my keyboard. That notice moved me from the line where the y is down below. Then I can type my 1, and I can hit the right arrow to get out of that little subscript. If I keep typing over there, if I do my tilde and keep going, then I'm going to keep working down in that little bit, and I don't want to be doing that. So I'm going to go to the right to get out of it. Then I'm going to hit my tilde. The tilde, you're going to hit shift, and it's right above the tab bar on the left side. So over to the left of the 1 on the top of your keyboard. That'll give you the squiggle. And then I'm doing standard form for quadratic, so I'm going to type AX. I'm going to do my caret, which is the shift and the 6 button, to put in my square. And then I'm going to hit to the right to get out of the superscript. And I'm again going to hold down shift and the underscore button, which is right beside the 0, to get down and put my 1 in. I'm then going to hit the right. I'm going to type plus BX subscript 1 to the right plus C. Okay, so I've input my equation, and now you'll notice that a bunch of information has popped up. It's also drawn a line on my scatter plot. It's showing me what it thinks is the best possible quadratic fit, quadratic curve for this data set. Now, a couple of things to notice here. Do you see where it says statistics R squared? You always want to look at this variable because it's going to help you if you're not 100% sure which function to be using. Do you see that it's a 0.9993 correlation? That means this is a pretty good guess that this quadratic line is fitting this data. You want this number to be as close as possible to 1. Watch what happens if I put in, let's say, oops, I forgot my subscript. Let's say I thought this one was linear. So I'm going to put mx with the subscript of 1 plus b. You'll notice here that it drew a line, this purple one, that doesn't go through very many points because it has to be a straight line. The r squared value is also closer to 0 than it is to 1, and that's because it's not a good fit. So I'm not going to use a linear model for this one. If I did the same thing, but this time I used exponential, so a, b raised to the x, with a subscript of 1, it's again giving me a line that doesn't really hit my data points very nicely. I am going to click log mode whenever I'm in exponential. The next one we'll talk about that a little more, but always click log mode. If I look at my r squared variable, I don't have a very good fit. This is 0.07, which is not very close to rounding up to 1. 0.999 is close to rounding up to 1. So that means then this is the model I'm going to use. The parameters down here are what give you your equation. So you'll notice that you have what A is equal to, what B is equal to, and what C is equal to. These numbers are the numbers that go in the A, B, C spots to our regression equation. So I'm going to write my regression equation, but I'm going to use A, B, and C. So for this problem, my regression equation is going to be y is equal to, because now this is for this specific one, it's not for programming in the approximation, and I'm going to round to 3 decimal places here. Desmos said negative 0.261 x squared. That was the A value. The B value was 22.591 x, and then the C value was 23.029. So that's A, B, and C all plugged into the standard form version of a quadratic equation. So that's my regression equation. All right. So the last thing that we need to do besides finding the regression equation is making a prediction for something that we don't have a data point on using our equation or using the graph in Desmos. So because I want to show you an exponential fit as well, rather than making a prediction based on this pumpkin catapult, let's go ahead and do this one. We're looking at the number of mold spores on a piece of bread after X amount of days in the pantry. So the number of days that it spends in the pantry is X, and the dependent variable is the number of spores that grow each of those days. All right, so I'm going to go back to Desmos. I'm going to clear out the work that I have. I'm going to add a new table again and start again. So I've got 2, 4, 6, it's counting for me. Oh, I hit down the arrows, remember, don't work. Hit enter, and then 10. For my y values, I've got 1, 2, 14, 19, 1595, and 1790. Okay, I'm again going to check my work and make sure I don't have any typos in those y values. I don't think I do. So I'm going to hit the Zoom Fit button. Now this looks like it could be linear, or we could just not have very much information and it could be exponential. So let's look at what we can do to compare the two. So I'm going to do the exponential one first. I'm going to do y sub 1 approximates a b raised to the x with a subscript of a 1. I'm going to hit log mode this time, and look at that r squared value. It's a perfect 1. That means it's a perfect fit for this data. That's a good sign that I'm looking in the right place. If I did the same thing but with a linear function with mx plus b, notice that this r squared value is good. It's 0.9955, but it's not as good as the r squared value of 1. So I am not going to use that linear model. Anytime you are not sure about which model to use, you can certainly try both. Just be sure you don't have any typos and be sure you're considering the context of the problem as well. If the numbers ought to go up and then come down or vice versa, then you're not going to be using linear or exponential. Okay, so now that we've got our log mode, we have a and b, so we can write our equation. Let's go look at these questions. Identify the parent function. That was exponential. And remember, our exponential equation or formula is a times b raised to the x power. And the parameters just gave us in Desmos our regression equation. So that's going to be y is equal to, let's see, we have 1000.68, that's my a, and then my b value, 1. You know what, let's go ahead and do 05993. Let's give all of the decimals there. That is the b. Remember, those values come from the parameters listed down here. Okay, so I have that, and now I'm asked to predict how many mold spores will there be after 20 days. Remember, days is an x value. So what I'm going to do in Desmos here is I'm going to start another line, and I'm going to say x is equal to 20, because that's going to give me where I'm looking for an intersection. So I am going to need to zoom out here because you can see I didn't see anything pop up on my graph. So as I zoom out, you'll see that this new line that goes through 20 is appearing. And I'm going to move my grid around, my graph around, until I see that intersection point. When I click on it, it's going to give me an ordered pair, 20 comma, and then the y value. And that's what I'm trying to find. How many mold spores are going to be there? Let's round to whole numbers for this one, because mold spores aren't going to come in fractional rates. So when x is 20, y is equal to 3,205. So I plugged in x is equal to what it was looking for, and when I found that intersection, that answered my how many question. So we figured out the parent function for a data set. We found the regression equation using Desmos, and then we used Desmos also to make predictions. So those three things now are what you're going to practice in the Now You Try.